This is the chapter review for Chapter 18, Sampling Distribution Models. So we start out here talking about proportions. And what we're going to get it with this chapter is that there is a known proportion. Chapter 18 is about a known proportion. So let's go down here and look at this. You see at the center right here is our known proportion. If we say that something should happen 50% of the time, right here at the center is 50% of the time. Now, just like with other models, we have a standard deviation, and that is described right here, as seen on the previous slide, as PQ over n square root. That's how we're describing the standard deviation for a sampling model for proportions. At the center, we have the known proportion, and then each standard deviation is plus 1 PQ over n square root. So we can figure out how odd something is, and we'll see that down here. If we expect 45%, this is our sample of people who believe in ghosts, 45% of people are expected to believe in ghosts, but in our sample we found 48. So if this is to be true, this little shaded area under here has a p-value, as we've learned later on, of 0.0175. That means there's a 1.75 chance out of 100 that this would just happen by chance if the true center is right here. And we apparently know that for this problem, that this is the true center. So it's important to understand what these problems are asking. You have a known proportion. A known proportion. This is like the apple problem for this chapter, where we know a certain percentage of the apples are bad in a truck. So what's the probability we will find greater than 8% apples bad if we know 5% of apples are bad? You can make up a lot of questions like this, as you can see right now as you look at this slide. In the question I just made up, 5%, where I'm hovering over right now, would be at the center. And what would be the probability we would find 8% bad? Well, that would be over here. So I might just reverse that. If we know that 5% are bad, right here, we can look at the probability of finding 8% bad or greater. Things like that. If we talk about another ghost problem, if it's true that 70% of Americans believe in ghosts, right here, would be 70 in the middle. What's the probability of finding over 50% of Americans believe in ghosts? We would look down here. Remember, your known proportion is at the center, and then you would put the mark and graph either way, just like you're doing a p-value. It's kind of like the same concept, but we're not exactly doing a hypothesis test here. So we scroll down a little further, we have some of the rules and we have the conditions. You can look at your condition sheet, but we'll go through them real quickly. We have independence and randomization. We have the 10% condition, and we also have the success-failure condition. That means there needs to be at least 10 successes and at least 10 failures. This can be described as NP and Q, because P and Q are the probability of success and the probability of failure, where N is the sample size. This will get you 10 successes or 10 failures when you multiply them out. Now we kind of change gears here, because we're going to go into the central limit theorem. What the central limit theorem suggests to us is that when we have an oddly shaped distribution, right here, the distribution is kind of flat. But when we sample from it, this is samples of 2 and then averaged out. This is sample of 3 and then averaged out. Like you take 3 dice and you roll them and you take the average of them and you plot that average. We go even further and you see it gets tighter and tighter. That's what the central limit theorem suggests, is that as we increase the sample size from a population, we will center around the true average and get tighter in. It's a very quick explanation of it. But this concept is used, and we can use it for means also. You just saw it for dice rolls. Now we're looking at tickets drawn, and as you watch as I do this, this is as we increase the number that we're averaging together, it gets a lot tighter. We finally end off here with a few models to help us understand this. Let's go down here all the way to the bottom. We saw here earlier some equations to use for proportions. We can also do it for means. Think right here. This is the same concept we just did with means. We're looking at a balcony where we know the balcony, where we know the average weight of a person is 176. What's the probability that 100 people will have a weight over 190, or in this instance underneath? Review this, check it out, good luck.